welcome back to Deep Somna. If you are here tonight, something brought you to this quiet place. Maybe the day was long, and your body knows it, even if your mind hasn't quite caught up. Maybe there are thoughts still circling, small things, large things, turning slowly in the background like something that forgot to stop. That's all right. You don't have to push them away. You don't have to fix them or finish them tonight. You only have to do one thing, and that thing is nothing at all. Just be here. Just let your weight settle into whatever is beneath you. Let your hands rest. Let your jaw loosen just a little. Tonight, we are going to think about galaxies. Not as a lesson, not as something to memorize or understand completely, just as something to drift through, the way you drift through a long and comfortable dream. Galaxies are among the largest structures in the known universe, enormous systems of stars and gas and dust and invisible matter, each one containing hundreds of billions of suns, each one ancient beyond any ordinary measure of time. They are the architecture of the cosmos. Everything we have ever seen, every star in the night sky, every planet, every nebula glowing softly in a telescope image, all of it belongs to a galaxy, including us. And yet, for all their scale, there is something inherently calming about thinking of galaxies. They move slowly. They change over timescales so vast that nothing in an ordinary human life could register the difference. They do not hurry. They do not react to urgency. They simply continue enormous and patient, following the quiet mathematics of gravity through the dark. Let that quality into the room with you for a moment. The patience of something incomprehensibly large, moving at the pace of billions of years. Whatever was pressing on you today, it is very small against that backdrop, not meaninglessly small, but small in a way that makes room for rest. Close your eyes, if they aren't already closed. Feel the surface beneath you, the weight of your body, the softness or firmness of where you lie. Take one breath in, slow and full, and let it go completely. Above you, right now, there is a ceiling. Above the ceiling is a roof. Above the roof is air, and above the sky, stretching outward in all directions at once, are galaxies, hundreds of billions of them, scattered across a space so vast that the numbers describing it stop meaning anything intuitive very quickly. If you represented the entire observable universe as a single sheet of paper, each galaxy would be smaller than a single atom on that page. There is no way to hold that in the mind as a real spatial experience, and that's fine. You are not meant to hold it. You are only meant to let it be there, beyond the ceiling, beyond the dark, enormous and quiet, and very, very old. Let's begin at the beginning, or as close to a beginning as we can reach. The universe, as best as cosmologists can determine from the evidence available, from the light of ancient galaxies, from the cosmic microwave background, from the behavior of matter and energy across vast distances, is approximately 13.5 billion years old. That number is so large it resists ordinary understanding, so let it be just a number. 13.8 billion years. A long time, longer than the Earth has existed, longer than the sun has burned, longer than almost anything we know of except the universe itself. In the earliest moments of its existence, fractions of a second after the Big Bang, a term that describes the rapid expansion of the universe from an extraordinarily hot and dense state, rather than an explosion in the usual sense. The universe was not yet a place where galaxies were possible. It was too hot, too energetic, too uniform. Matter and energy were interchangeable and chaotic. There were no atoms yet, let alone stars. There were only elementary particles, quarks, photons, electrons, in a blazing dense soup that filled all of space. As the universe expanded, it cooled. After a few minutes, protons and neutrons combined to form the first atomic nuclei, mostly hydrogen, with some helium and a trace of lithium. But it was still too hot for electrons to attach to those nuclei and form complete atoms. The universe was a glowing plasma, opaque to light, dense and luminous, and then, roughly 380,000 years after the Big Bang, the universe cooled past a critical temperature. The electrons finally settled onto the nuclei. Atoms formed, and in that moment, the universe became transparent for the first time. Light could travel freely through space without being immediately absorbed. The glow of that moment, that first release of light, has been traveling ever since, in all directions. And today we detect it as the cosmic microwave background radiation, a faint, almost perfectly uniform warmth filling the entire sky, a kind of afterglow from the universe's early childhood. It is the oldest light we can observe. But after that moment of transparency, something strange happened. The universe went dark again, not because light stopped traveling, but because there were, for a long time, no sources of new light. The atoms were there, hydrogen and helium, slowly drifting, cooling further, drawn together by the gentlest possible gradients in gravity. But no stars had formed yet, no galaxies, just an expanding cloud of gas, growing slowly thinner as the universe stretched, falling gradually toward the places where the gas was very slightly denser than average. Astronomers call this era the cosmic dark ages. It lasted, roughly, from about 380,000 years after the Big Bang to perhaps 200 or 300 million years after. A stretch of time longer than the current age of Earth, during which the universe existed in quiet, complete darkness. In that darkness, though, something was being prepared. The gas was not perfectly uniform. There were tiny ripples, fluctuations in density, seeded in the earliest instance of the universe by quantum effects during a period of extraordinarily rapid expansion called inflation. These fluctuations were almost unimaginably small. The universe was not quite perfectly smooth, and gravity, patient and relentless, began to amplify those tiny differences. The regions that were ever so slightly denser pulled in a little more gas. They grew a little denser still. The regions that were slightly less dense gave up their gas and became emptier over hundreds of millions of years. This slow gravitational sculpting transformed the featureless gas into structure. Long sheets and threads of matter condensed, while vast regions in between were emptied. A pattern emerged, a vast, three-dimensional web of filaments and nodes and enormous voids, all built from the same uniform gas, shaped entirely by the slow, patient force of gravity. And where that gas compressed most tightly, at the dense intersections of those forming filaments, something remarkable happened. The first stars ignited. Let your breath be slow and natural for a moment. Just let that image rest in your mind, not as something to analyze, but as something to see gently from a distance. A long cosmic darkness, and then one by one, and then in growing swarms, the first lights coming on. Stars burning for the first time in a universe that had been dark for hundreds of millions of years. These first stars were not like the stars we know today. They were enormous, some of the most massive stars that have ever existed. They had no heavy elements, because heavy elements are made inside stars and then scattered by stellar explosions, and none of that had happened yet. They were made almost entirely of hydrogen and helium, burning hot and fast and brilliantly. They may have lived only a few million years before dying in catastrophic explosions, seeding their surroundings with the first generation of heavier elements: carbon, oxygen, iron, the raw materials from which everything more complex would eventually be built. Those first stars were also the first members of the first galaxies. The earliest galaxies were not grand spirals. They were small, compact, irregular, little more than dense clusters of young stars huddled together in the gravitational embrace of a dark matter halo. Dark matter, a mysterious substance that we will return to many times tonight, because it underlies almost everything about how galaxies work, had already been present since very early times, and its gravitational wells provided the scaffolding that allowed the first stars and galaxies to form at all. These early galaxies were chaotic and active. They formed stars at ferocious rates, burning through gas quickly, blazing intensely in ultraviolet light. Some of them collided with their neighbors almost immediately. The early universe was dense enough, and the early galaxies close enough together, that interactions were common. When two small early galaxies merged, the gas was compressed, more stars formed, and the resulting system grew a little larger, and then that slightly larger system found another neighbor, and merged again. This process of small galaxies merging into larger ones, over and over, across billions of years, is called hierarchical assembly, and it is the fundamental story of how the galaxies we see today came to be. The Milky Way did not spring into existence fully formed. It grew, slowly, through a long history of gravitational encounters, of smaller companions falling in, of gas being drawn from the surrounding cosmic web. The grand spiral we inhabit today is the product of billions of years of patient accumulation. You can let that image drift through your mind without holding it tightly. The galaxy is something that grew, not designed, not sudden, but gradual, organic in its own strange way, built through time and gravity, and the slow dance of matter in the dark. Let your body be heavy now. Let the muscles in your legs relax. Let the muscles across your back soften a little. There is nowhere to go and nothing to do. Just the darkness of your room, and the much larger darkness beyond it, and somewhere in that darkness, the slow and patient turning of 100 billion galaxies. The Milky Way, the galaxy we live in, is, by many measures, unremarkable. That word is not meant as a diminishment. It means rather that the Milky Way is a fairly typical large spiral galaxy. Not among the very smallest, not unusually young or unusually old, not exceptionally active or exceptionally quiet. It is, in a certain sense, an average member of a very large family. It is a barred spiral galaxy. In the center, where most of the oldest and most densely packed stars live, there is a bulge, a rounded concentration of billions of ancient stars. Running through the center of that bulge is a structure astronomers call a bar, an elongated, roughly rectangular arrangement of stars that extends outward from the central hub. From the ends of the bar, 2 or 4 large spiral arms sweep outward in graceful curves, trailing streams of stars and gas and dust into the plane of the galaxy. The Milky Way spans roughly 100,000 light-years from edge to edge. A light-year is the distance that light, moving at nearly 300,000 kilometers per second, the fastest anything in the universe can travel, covers in 1 year. 100,000 of those years end to end. If you could somehow build a spaceship that traveled at the speed of light and pointed it from one edge of the Milky Way to the other, your journey would take 100,000 years. Our solar system sits about 26,000 light-years from the center, just over halfway out, in a relatively quiet region between 2 of the larger spiral arms. It is not a prominent address. We are not near the center, not near the edge, not in any particularly distinguished location. We orbit the galactic center at roughly 220 kilometers per second, moving incredibly fast by any human measure, and yet requiring about 225 million years to complete a single circuit of the galaxy. That is 1 galactic year, 1 trip around the Milky Way. The last time our solar system was in approximately the same position in its orbit, the most complex life on Earth was the early ancestors of the dinosaurs. We have been around the galaxy exactly 20 times since Earth formed. In the full lifetime of the Milky Way, perhaps 50 such circuits have passed. Let that scale settle gently, not with anxiety, not with dizziness, just with a soft recognition of how large time is, how patient the universe is, how much has happened and is still happening at a pace too slow for any individual life to perceive directly. You exist inside this galaxy right now, not outside it, looking in, but inside, embedded in it, one small point of warmth and awareness carried along in the spiral arm of a turning wheel that has been turning for 10 billion years. The Milky Way contains somewhere between 200 billion and 400 billion stars. The uncertainty in that number reflects the genuine difficulty of counting stars spread across a space this vast, many of them hidden behind thick clouds of dust, many too faint to detect individually even with our best telescopes. What we can say is that most of those stars are smaller and dimmer than our sun, red dwarf stars, burning slowly and steadily for trillions of years, far longer than the current age of the universe. Many of them almost certainly have planets. Some of those planets almost certainly have conditions suitable, in some sense, for liquid water. The number of potentially habitable worlds in the Milky Way alone is probably in the billions. We don't know if any of them harbor life. That question is genuinely open. We have found, in the past few decades, that planets are extraordinarily common. Virtually every star seems to have them, in a variety of sizes and orbits. But whether life has arisen elsewhere, whether it has ever developed the ability to wonder about its own place in the universe, we do not know. The silence of the cosmos on this point is profound, and the question remains one of the most open in all of science. But for tonight, you don't need to resolve it. You can simply let the image of the Milky Way rest in your mind an island of 200 billion suns, slowly turning, embedded in a dark matter halo invisible to any telescope, carrying along with it this small planet and this particular night, and you, lying still and breathing quietly, somewhere inside one of its spiral arms. Your breath is slower now, perhaps. Let it be as slow as it wants to be. We will keep drifting, gently. There is no hurry. There never was. Now let's step outside the Milky Way, not literally, not physically, but in imagination. Let's rise above it and look back, the way a very, very slow spacecraft might if it traveled for millions of years in the right direction. From that imagined distance, the Milky Way would appear as a flat, glowing disk, a pale blue-white center brightening toward the core, and then the spiral arms curving outward through the thin edges of the disk, fading gradually into a diffuse outer halo. And nearby, relatively nearby, on this cosmic scale, you would see other galaxies. The Milky Way is not alone. It belongs to a gravitationally bound collection of galaxies called the local group. The local group contains more than 50 known members, though most are small and faint. Dwarf galaxies containing a few million to a few billion stars, orbiting the two larger members like moons around planets. Those two larger members are the Milky Way and Andromeda. Andromeda, also known by its catalog designation Messier 31, is a spiral galaxy roughly 2.5 million light-years away. That sounds like an enormous distance, and by any human measure it is, but on the scale of the broader universe it is practically a neighbor. Andromeda is broadly similar to the Milky Way in structure, a flat spiral disk with a bulge at the center, but somewhat larger. It contains an estimated trillion stars, roughly twice as many as the Milky Way. True of it is roughly twice as many as the Milky Way. Its central black hole is correspondingly more massive. On a very clear, very dark night, far from city lights, Andromeda is visible to the naked human eye. It appears as a faint, elongated smear of light in the constellation named for it, the most people will ever see without optical aid. What that faint smear represents, when you know what you're looking at, is the accumulated light of a trillion stars, light that left Andromeda 2.5 million years ago, before any member of the genus Homo walked the Earth, traveling through the expanding void between us, before arriving at your eye on a quiet night. That light was already on its way to you, before your species existed. You don't need to do anything with that fact. Just let it rest there, soft and large, at the edge of sleep. The local group with its 50+ galaxies is itself just one small piece of a much larger structure. The local group belongs to a supercluster, an enormous, loosely bound association of galaxy groups and clusters called Laniakea. The name comes from the Hawaiian words for immeasurable heaven. Laniakea stretches more than 500 million light-years across and contains roughly 100,000 galaxies. Our tiny local group is a peripheral member, sitting in one of the outer filaments of this vast structure. And Laniakea is not the only supercluster. The observable universe, the portion of space from which light has had time to reach us since the Big Bang, contains perhaps 2 trillion galaxies in total, distributed across the cosmic web in a pattern of extraordinary complexity and quietness. 2 trillion galaxies, each one containing hundreds of billions of stars. Let the number drift through without trying to hold it. It is beyond holding. It is simply the scale of things. Your breathing is easy and slow. Your body is resting. Let your thoughts soften at the edges, like mist beginning to thin in morning light. The universe is out there, enormous and patient, doing what it has always done, and you are here, in the dark, in the gentle and necessary act of rest. We will continue, softly, into the deeper questions of what holds all of this together. Most of the universe is invisible. This is not a poetic exaggeration. It is one of the most firmly established conclusions in modern cosmology, supported by multiple independent lines of evidence gathered over decades of careful observation. The atoms, ordinary matter, the stuff of which stars and planets and gas clouds and people are made, account for only about 5% of the total energy content of the universe. The remaining 95% is divided between two mysterious entities. Dark matter, comprising roughly 27%, and dark energy, making up the remaining 68. Neither of these has been directly detected. Neither is made of anything we have identified in a laboratory. And yet both are absolutely central to why the universe looks the way it does, why galaxies exist in the forms they take, why the cosmic web has the structure it has, why the universe is still expanding, and doing so at an accelerating rate. Let's begin with dark matter, because it is woven into everything about how galaxies form and survive. Dark matter does not emit light. It does not absorb light. It does not interact with ordinary matter in any way that our current instruments can directly detect. With one exception, it has mass, and mass exerts gravity. The presence of dark matter reveals itself entirely through its gravitational effects on the visible things around it, on the motion of stars within galaxies, on the bending of light passing near massive structures, on the large-scale distribution of galaxies across the cosmic web. The story of how we came to understand that dark matter exists is one of the quieter revolutions in the history of science. It did not begin with a dramatic announcement or a single decisive experiment. It accumulated over decades, as observation after observation showed that something was missing from the calculations. One of the most significant contributors to that understanding was an American astronomer named Vera Rubin. Working in the 1960s and 1970s, Rubin spent years measuring the rotation of spiral galaxies, specifically, how fast different parts of a galaxy were moving as they orbited the center. Based on standard gravitational physics, you would expect the stars at the outer edges of a galaxy to orbit more slowly than the stars closer to the center, because they are farther from the concentrated mass at the core. This is how our solar system works. The outer planets orbit more slowly than the inner ones. What Rubin found, galaxy after galaxy, was that this was not happening. The outer stars were not slowing down. Their orbital speeds were roughly the same as those of the stars much closer to the center. In some cases, the speeds were even slightly higher at the edges than standard calculations predicted. This should not have been possible, based on the visible mass of those galaxies. The stars and gas clouds that could be seen and measured simply did not contain enough mass to keep the outer stars in their orbits at those speeds. Something was providing extra gravitational pull, something invisible, distributed throughout, and beyond the visible disk of the galaxy, providing a diffuse but massive gravitational halo that held the spinning stars in place. That something is what we call dark matter. The The simplest way to picture it is as an enormous, diffuse sphere of invisible mass surrounding every large galaxy, extending far beyond the visible stars, enveloping the visible disk the way a soap bubble might envelop a coin. This halo is not sharply bounded. It fades gradually with distance from the center. But it is vast. The dark matter halo of the Milky Way extends perhaps 5 to 10 times farther than the visible galaxy itself, in every direction. And without it, the Milky Way would not hold together. The outer stars would gradually drift away from their orbits. The galaxy would slowly come apart over billions of years. The halo is not decoration. It is the structural foundation. Let your body sink a little deeper into stillness. Feel the weight of your arms. Feel the rise and fall of your chest with each slow breath. There is no urgency here. Just the quiet image of the Milky Way, held together by something enormous and invisible, turning patiently in the dark. The evidence for dark matter is not limited to galaxy rotation. It comes from multiple independent sources, and each one points to the same conclusion. One of the most striking pieces of evidence comes from gravitational lensing, the way that massive objects bend the path of light passing near them. This effect was predicted by Einstein's general theory of relativity and confirmed through observation. When a very massive galaxy or cluster of galaxies lies between us and a more distant object, the gravity of the foreground mass bends the light from the background object, distorting and sometimes multiplying its image. By measuring how much the light is bent, how dramatically the background object is distorted, astronomers can calculate the total mass of the foreground object, including mass that cannot be seen directly. When this calculation is done for galaxy clusters, the result is always the same. The visible mass, all the stars and gas in all the galaxies in the cluster, is far less than the mass required to produce the observed lensing effect. There is typically 5 to 10 times more mass present than can be accounted for by anything visible. That extra mass is dark matter. One of the most compelling demonstrations of this came from an event called the Bullet Cluster. Two galaxy clusters that passed through each other about 150 million years ago. When the clusters collided, the hot gas in each one, which makes up most of the ordinary matter in galaxy clusters, slowed down due to pressure and electromagnetic interactions between the two gas clouds. But the dark matter, which interacts only gravitationally and not electromagnetically, passed right through without slowing, continuing on past the gas. The result was a clear spatial separation. The dark matter ended up ahead of the gas in a way that could be mapped by the gravitational lensing it produced. It was one of the clearest, most direct demonstrations that dark matter is real and distinct from ordinary matter. The two components of the cluster literally separated in space, allowing astronomers to see them independently for the first time. Despite all of this indirect evidence, despite the confidence with which cosmologists incorporate dark matter into their models, no one has yet detected a dark matter particle directly. This is one of the defining open questions in physics. Various candidates have been proposed. Among the most discussed are WIMPs, weakly interacting massive particles, hypothetical particles with masses perhaps 10 to 100 times that of a proton, interacting with ordinary matter through the weak nuclear force, so rarely that trillions of them could pass through a human body every second without any interaction at all. To search for them, Physicists have built extraordinarily sensitive detectors in deep underground laboratories, shielded from the constant background of cosmic rays and other radiation that would otherwise overwhelm any faint signal. These detectors, sometimes made of ultra-pure germanium or xenon, cooled to temperatures near absolute zero, wait in the quiet dark for the almost impossibly rare event of a dark matter particle stopping inside them. They have been waiting for years, decades, in some cases, and so far they have not found a whim. This is not a failure of patience or technique. Each generation of detectors is more sensitive than the last. Each non-detection tells us something, that if whims exist, they must interact even more weakly than the most optimistic models predicted. The circle of possibility is narrowing, slowly and carefully. Another candidate is the action, a particle proposed in the 1970s for reasons having nothing to do with dark matter, related to a puzzle in the physics of the strong nuclear force. Actions, if they exist, would be extraordinarily light, millions of times lighter than an electron, and almost completely non-interacting. They would be produced in enormous numbers in the early universe, forming a kind of cold, diffuse cosmic fluid. Experiments to detect actions typically involve placing highly sensitive equipment inside strong magnetic fields, hoping to catch the rare event where an action converts into a faint photon of microwave radiation. These experiments require extraordinary patience and precision. There are other ideas too: sterile neutrinos, primordial black holes formed before any stars existed, exotic particles that fall outside all current theoretical frameworks. The honest answer is that we do not know what dark matter is made of, and there is something worth sitting with in that honesty. The most carefully and extensively studied piece of the universe, visible matter, atoms, everything we can touch and see and measure directly, represents only 5% of what exists. The rest is a mystery that 5 decades of intensive scientific effort have not resolved. The universe is mostly something we don't understand. That is not frightening. It is, in a deep sense, freeing. The universe is not finished being known. There is more to learn than has ever been learned. And that means that what seems complete and settled can always expand, always deepen, always open into something more surprising than what came before. Your breath is slow and quiet. Let the thought of dark matter drift through your mind like a shadow passing behind a lamp, present, shaping the light around it, but itself unseen. Not mysterious in a frightening way. Not mysterious in a frightening way, just quietly, gently unknown. Now let's think about the other great mystery of the cosmos, the force that shapes not just galaxies, but the fate of the universe itself. In the late 1990s, 2 independent teams of astronomers were studying a particular type of stellar explosion called a Type Ia supernova. These explosions are useful to cosmologists because they all have roughly the same intrinsic brightness. They function as what astronomers call standard candles. If you know how bright something actually is, you can calculate how far away it is from how bright it appears. By measuring the apparent brightness of Type Ia supernovae at various distances, the teams hoped to measure how the expansion of the universe had been decelerating over time. Gravity should have been gradually slowing the expansion since the Big Bang, and measuring supernovae would reveal the rate of that slowdown. What they found instead was the exact opposite. The distant supernovae were fainter than expected. They were farther away than they should have been if the expansion were simply coasting at a constant rate or slowing down. The universe was not decelerating, it was accelerating. The expansion of space was speeding up. Both teams arrived at this conclusion independently, using different data and different methods, and reached the same startling answer. The universe is not just expanding, it is expanding faster and faster, driven by something that has no satisfactory explanation in any current theory of physics. That something is called dark energy. Dark energy is even more mysterious than dark matter in a certain way. Dark matter at least behaves like matter. It has mass, it clusters, it falls into gravitational wells and builds structure. Dark energy does not. It is associated with empty space itself. It is present everywhere, uniformly, even in regions where there is no matter at all. And rather than pulling inward like gravity, it pushes outward, driving space itself to expand at an accelerating rate. One mathematical description of dark energy is Einstein's cosmological constant, a term Einstein originally introduced into his equations of general relativity in 1917, for a completely different reason, and which he later doubted. When the acceleration of the universe was discovered, that same mathematical term returned as a possible description of the phenomenon. Whether the cosmological constant is the right framework, or whether dark energy is something more dynamic, a field that changes over time, perhaps, is still unknown. What is known is that dark energy, whatever it is, will continue to drive the expansion of the universe. Over time, not millions of years, but billions of years, the galaxies beyond our local group will recede farther and farther. The light from more and more distant galaxies will be stretched to longer and longer wavelengths, redshifted past the point where our instruments can detect them. Eventually, most of the universe will slip beyond our cosmological horizon, the boundary beyond which the expansion of space prevents light from ever reaching us. In the very far future, a hypothetical observer in the Milky Way, or in whatever the Milky Way will have become by then, would look out at a universe that appeared to contain only the local group. All the rest, all 2 trillion galaxies of the observable universe as we know it today, would be invisible, their light unable to reach across the expanding void. We happen to live at a particular moment in cosmic history, when the universe is still young enough that we can see all the way back to its earliest epochs. The James Webb Space Telescope, orbiting about 1.5 million kilometers from Earth, is capable of observing galaxies from when the universe was only a few 100 million years old. The window is open right now, and astronomers are using it, carefully and patiently, gathering light that began its journey before the Earth existed. That window will remain open for a very long time, but not forever. And there is something quietly moving about that. About living in the era when the universe is still fully visible to us, still readable, still telling its story across the full span of cosmic time. You don't need to feel urgency about it. That is not the feeling it calls for. It calls for something softer, a quiet appreciation that tonight, above your ceiling, the light of 2 trillion galaxies is still falling freely through space, some of it reaching the instruments of observatories on mountaintops and in orbit, carrying information from the beginning of time. It is a very good night to rest. Let your body settle. Let your breathing continue at whatever pace it has found, easy and natural and slow. The things you were worrying about earlier today are very far from this moment now. They belong to a different scale, and this scale, this cosmic scale, vast and patient and indifferent to urgency, can hold hold you gently while you drift. We will keep going into the lives of galaxies, into their structures and their histories and the quiet drama of how they change. Inside every large galaxy, at its very center, there is a supermassive black hole. A supermassive black hole is not simply a very large version of the black holes formed when massive stars collapse at the ends of their lives. Those stellar mass black holes might contain a few times the mass of our Sun. Supermassive black holes are in a different category entirely. The one at the center of the Milky Way, known as Sagittarius A star, has a mass of approximately 4 million times that of our Sun. The one at the center of the Andromeda Galaxy is larger still. Estimates suggest it may contain more than 100 million solar masses. And in some of the largest galaxies in the universe, the central black holes contain tens of billions of solar masses. How black holes this massive form is itself an interesting question, without a fully satisfying answer. They may have grown from smaller black holes present in the early universe, feeding on gas and merging with other black holes as their host galaxies grew. They may have formed through the direct collapse of enormous gas clouds in the early universe, bypassing the normal stellar evolution pathway entirely. The mechanisms are still debated. What is clear is that they are present at the centers of virtually every large galaxy, and that they play a profound role in shaping the galaxies around them. When a supermassive black hole is actively feeding, pulling in gas from the surrounding region, heating it to extreme temperatures as it spirals inward, it can release enormous amounts of energy. In its most extreme form, this process produces what is called a quasar, an object so luminous that it outshines the entire galaxy of hundreds of billions of stars that surrounds it. Quasars were first identified in the early 1960s as point-like sources of intense radio and visible light at enormous distances. So luminous, in fact, that astronomers initially had difficulty believing they were real objects rather than measurement errors. Quasars are rare in the nearby universe. Most of the galaxies we observe in our cosmic neighborhood, including the Milky Way, have supermassive black holes that are currently quiet, not actively consuming large amounts of gas, not producing quasar-level luminosity, but looking further out in distance, and therefore further back in time. Quasars are much more common. The early universe, when galaxies were younger and richer in gas, was a brighter, more turbulent place. Many of the supermassive black holes that are quiet today blazed as quasars in the distant past. The Milky Way's own central black hole shows signs of past activity. Structures called the Fermi bubbles, two enormous lobes of gamma-ray emission extending tens of thousands of light-years above and below the galactic plane, are thought to be the remnants of a powerful outburst from Sagittarius A star that occurred perhaps a few million years ago. At that time, our galaxy's center may have been as luminous as a low-level quasar. Now it is quiet, waiting, occasionally flaring briefly as small amounts of gas are captured, but nothing like its past brilliance. What goes on at the center of a galaxy? Whether the central black hole is fed or starved, active or quiet, has consequences for the entire galaxy around it. When a quasar blazes, its radiation and powerful particle jets heat the surrounding gas and sometimes drive it out of the galaxy entirely. This can stop star formation, the process by which gas clouds collapse under gravity to form new stars. Because the gas needed for star formation has been heated too much to collapse or expelled altogether. this way, a central black hole can regulate its own feeding. As it grows, it affects the gas supply that feeds it. The galaxy and its black hole are in dialogue in a sense, shaping each other's evolution over billions of years. Let your eyes stay closed. Let the image of that inner galaxy drift gently through your mind. A bright, dense center where ancient stars orbit a massive invisible gravity well, and further out, the long sweeping arms of stars and gas slowly turning. No urgency in any of it. Just slow, vast, patient motion. One of the deep and somewhat humbling things about the study of galaxies is how much of it is still genuinely uncertain. Not in a discouraging way, but in the way that honest science always is, open at the edges, full of questions that have been precisely articulated but not yet answered. The more carefully we look, the more we find that we had underestimated the complexity. Take the question of how galaxies stop forming stars. The galaxy that is actively forming stars is full of cold, dense gas, enormous clouds of hydrogen and helium, compressed under their own weight, collapsing slowly into new suns. These star-forming regions glow with the light of young, hot, massive stars just come into being. Surrounded by the nebulae they are ionizing, it is some of the most visually striking material in the cosmos, and it speaks of an ongoing vitality, a galaxy still actively building itself. But over time, many galaxies stop. They exhaust their supply of cold gas, or they have it stripped away, or it is heated by feedback from the central black hole, or blasted out by the winds of massive dying stars. The galaxy transitions from what astronomers sometimes call a blue, star-forming galaxy, blue because new, hot stars are blue, to a red, passive one, red because the hot young stars have died and only the older, cooler ones remain, glowing with a warm, steady, quiet light. This transition, called quenching, is one of the central puzzles of galaxy evolution. When does it happen? What triggers it? Why do some galaxies quench early, when the universe is still young, while others continue forming stars for many billions of years? Why does the rate of star formation in the universe as a whole peak around 10 billion years ago and decline since then? These questions have partial answers. The environment matters. A galaxy falling into a dense cluster can have its cold gas stripped away by the hot plasma that fills the space between cluster galaxies, a process called ram pressure stripping. And without that cold gas, it can no longer form new stars. The central black hole matters. Its feedback can heat or expel gas. The simple consumption of available gas matters. But the full picture of how all these processes interact, and which ones dominate in which galaxies at which times, is still being worked out. There are ongoing surveys. The Dark Energy Spectroscopic Instrument, for example, mapping millions of galaxies and measuring their spectra to determine their distances, velocities, and the properties of the stars within them, that are helping to build a statistical understanding of how galaxies change over cosmic time by comparing galaxies at different distances and therefore different ages. Astronomers can trace the history of the galaxy population as a whole and begin to identify which processes dominate at which epochs. This is patient, cumulative work. It does not produce dramatic single announcements. It produces a slowly sharpening picture, built year by year from the accumulation of data and and the steady refinement of models. Science at this scale is not done in flashes. It is done in the way that all deep understanding is built carefully, collaboratively, across generations. Let the feeling of that slow, patient work accompany you for a moment. Somewhere right now, telescopes are turning. Data is being recorded. Astronomers are reading spectra, measuring redshifts, comparing observations to models. The project of understanding how galaxies form and evolve is ongoing at this very moment. While you lie still in the dark, there is something calming about that. The universe does not wait for urgency. The telescopes do not hurry. The photons arrive at whatever rate they arrive, and the detectors record them without rushing. It is a kind of patience that has no equivalent in daily life, and perhaps, in some small way, resting quietly in the dark is a participation in that same quality. Not frantic, not pressured, just present. Let your thoughts be easy now. Let your breath be easy. We will keep drifting. Galaxies are social creatures, in the sense that they very rarely exist in complete isolation. Most are members of groups or clusters, gravitationally bound collections of galaxies ranging from a few members to thousands. And the interactions within these collections are central to the lives of the galaxies involved. When two galaxies approach each other and interact gravitationally, the results can be quite dramatic. Even though the process is extraordinarily slow, the interaction between two large spiral galaxies unfolds over hundreds of millions to a billion years. Beginning when the outer edges of their dark matter halos first begin to feel each other's gravity, and ending, eventually, when the two systems have fully merged into a single new galaxy. The early stages are visually striking. As the two galaxies draw close, the gravitational tidal forces they exert on each other begin to pull material from the outer regions of each galaxy into long, graceful arcs. These tidal tails, streamers of stars and gas, stretched by the competing gravitational fields, can extend for hundreds of thousands of light years, sometimes looping entirely around both galaxies in beautiful sweeping curves. Some of the most aesthetically remarkable images captured by the Hubble Space Telescope show interacting galaxy pairs in exactly this stage. Their original spiral structures distorted by tidal forces, long tails of stars spiraling through space around them. As the two galaxies begin to pass through each other, and through they do pass, because even though a galaxy contains hundreds of billions of stars, those stars are so far apart that the probability of two individual stars colliding during a galactic merger is negligibly small. The gas clouds in the two systems collide directly. Gas, unlike stars, interacts hydrodynamically. When two gas clouds slam into each other, they compress. And compressed gas collapses under gravity and forms new stars. This surge in star formation, triggered by the compression of gas during a merger, is called a starburst. Starburst galaxies can form new stars at rates hundreds or even thousands of times greater than the normal quiet rate of a galaxy like the Milky Way, which produces perhaps 1 or 2 solar masses of new stars per year. During a major merger, hundreds of solar masses of new stars per year might form, briefly lighting up the system with intense blue-white radiation, and filling it with the nebulae of ionized gas surrounding newborn stars. But starbursts cannot last. They consume their gas quickly. The newly formed massive stars, which drive much of the burst's luminosity, have short lives. They burn burn for only a few million years before exploding as supernovae, releasing enormous energies that further stir and heat the gas, limiting further star formation. Within a few 100 million years, brief by cosmic standards, the burst fades. What is left after a major merger depends on the masses and properties of the two original galaxies. If two large spirals of roughly equal mass merge, the organized rotating structure of both disks is typically scrambled. The stars that had been moving in ordered orbits within the disk are now on random, looping paths in every direction. The resulting galaxy is smooth and rounded, an elliptical galaxy with little gas and little ongoing star formation. Its light is even and warm, dominated by older stars. It has lost the grand architecture of its spiral origins. Many of the largest galaxies in the universe, the enormous ellipticals that sit at the centers of rich galaxy clusters, are thought to have grown to their present size through exactly this process. Merger after merger, each one adding mass and stars, each one further smoothing the structure, until the result is a colossal, ancient, quiet system containing more stars than many individual galaxies combined. Imagine a vast, smooth sphere of ancient light, stars moving in random paths, unordered, not rushing in any particular direction, no spiral arms, no active star formation, just an enormous luminous cloud of old suns, orbiting slowly in every direction, held together by gravity and dark matter. Still, patient, ancient, there is a particular quality to that image that seems right for the end of a long day. Something that has grown through turbulence and is now, at last, quiet. Something that has no more urgency in it, just light and gravity and time. Let that image settle around you. Now let's spend some time with the large-scale structure of the universe, the pattern of how galaxies are arranged across the vast spaces between them. Because this pattern is one of the most extraordinary things science has discovered, and yet it has a quality about it that is deeply, fundamentally calm. When astronomers first began mapping the positions of galaxies in 3 dimensions, plotting their distances as well as their positions in the sky, they expected to find something roughly uniform. Galaxies scattered more or less evenly through space, perhaps with some clustering but nothing dramatic. What they found instead was something that took years to fully appreciate. Galaxies are not scattered randomly. They are organized into a web, the cosmic web, as it is now called, consists of long, thin filaments of galaxies stretching across hundreds of millions of light years, connected at dense nodes where the filaments intersect, surrounding enormous empty regions called voids. The voids are vast. Some are hundreds of millions of light years across, and within them, almost nothing exists. Just a few stray galaxies, an almost empty silence of dark matter and diffuse gas. The filaments are where the action is. Galaxies crowd along them, drawn by the gravity of the dark matter that forms their invisible backbone. At the intersections of filaments, the nodes, sometimes called galaxy clusters, hundreds or thousands of galaxies collect, bound together by their mutual gravity. When visualized in 3 dimensions, the cosmic web looks something like the inside of a sponge, or the network of neurons in a brain, or the structure of a crystal foam. These resemblances are superficial and should not be overinterpreted. But they do capture something real about the topology of the structure. a thin, connected network of material surrounding large, empty spaces. Almost all the matter in the universe is concentrated in that thin network. Almost all the volume is empty. This structure grew from the same tiny ripples in density that we discussed earlier, those quantum fluctuations from the inflationary epoch of the early universe, imprinted in the distribution of matter in the first fraction of a second after the Big Bang. Over 13 billion years of gravitational amplification, those tiny ripples grew into the filaments and clusters and voids of the cosmic web. The pattern we see today is the fingerprint of conditions in the universe's earliest moments, stretched and amplified by time and gravity into something enormous. By measuring the statistical properties of the cosmic web, the typical spacing between galaxy clusters, the sizes of voids, the correlations in galaxy positions across different scales, cosmologists can probe the fundamental parameters of the universe. Its total matter content, the fraction that is dark matter versus ordinary matter, the influence of dark energy on how structure grew over time. These measurements are among the most precise tools available for testing models of cosmology. Surveys like the Baryon Oscillation Spectroscopic Survey have mapped millions of galaxies across a significant fraction of the observable universe, measuring the positions and redshifts of each with careful precision. From those maps, patterns emerge, tiny, statistically measurable oscillations in the density of galaxies at a particular scale, an echo of sound waves that propagated through the early universe in the first few 100,000 years after the Big Bang. By measuring where those echoes are today, cosmologists can measure the geometry of space and the history of cosmic expansion. It is remarkable that the universe left such a legible record of its earliest moments, and that we, with our instruments and our patience and our mathematics, are capable of reading it. Let your breath be soft. Let the image of the cosmic web drift through your mind like something seen in deep water, vast, faintly luminous, threaded with filaments of light and separated by enormous dark spaces. Not frightening, just large, very old, very quiet. The galaxies within that web are not static. They move, drifting along filaments, falling toward clusters, orbiting within groups. The local group, our own small galactic neighborhood, is itself in motion. The Milky Way and Andromeda, and the other 50-some members of the local group, are all moving together through space, slowly falling toward the center of the Virgo supercluster, one of the larger structures in the Laniakea supercluster, and Laniakea itself is being drawn in a particular direction, toward a dense concentration of mass called the Great Attractor, a region of the universe where several large superclusters coincide. These motions are slow by everyday standards. The Milky Way is moving toward the Andromeda galaxy at roughly 110 kilometers per second, roughly 100 times the speed of a spacecraft leaving Earth, and yet far too slow to close the 2.5 million light-year gap in anything less than billions of years. The local group as a whole moves at several hundred kilometers per second relative to the cosmic background. At this pace, movements that matter cosmically happen over times that span millions of years. And yet they are happening. Right now, the galaxies are moving. The cosmic web is evolving. Structure continues to grow, slowly as smaller clusters fall into larger ones, and filaments continue to feed matter into the densest nodes. In the very long run, the expansion of the universe driven by dark energy will will ultimately overcome local gravitational attraction for all but the most tightly bound systems. The Virgo cluster will remain bound. Laniakea will not. Its outer parts will eventually be pulled away by the expansion. But for billions of years yet, the cosmic web will continue to evolve and grow, building ever larger structures in the regions where gravity can still hold matter together. You don't need to track all of this. Let it be part of the background, a sense of a vast, slow, ongoing process, happening at scales and timescales that make your present moment feel very small and very safe. You are here. The universe is doing what it does. And tonight, your only task is to rest. Let your thoughts continue to soften. Let the edges of things blur a little. We are moving toward the end of this journey. Slowly, the way galaxies move, without hurry, following the quiet pull of wherever you need to go. Now let's linger for a little while with the variety of galactic forms, the stranger, quieter members of the galactic family that don't fit neatly into the most familiar categories. There are galaxies so diffuse they are almost impossible to see. These are called ultra-diffuse galaxies, and they were only discovered relatively recently, when telescope technology became sensitive enough to detect their ghostly, low-surface brightness glow. An ultra-diffuse galaxy may span an area as large as the Milky Way, but contain only a tiny fraction of the stars. Its stars are spread out so thinly across such a large volume of space that the galaxy appears as nothing more than a faint, nearly featureless smear of light in the most sensitive deep sky images. Against the background of the sky, they are barely distinguishable from noise. What are they? Astronomers are still working this out. Some may be failed galaxies, systems that began to form but lost their gas before they could build many stars, perhaps expelled by the feedback of a central black hole, or stripped by a nearby larger galaxy. Others may have been normal galaxies that were tidally stretched and disrupted by interactions. Their stars spread out over enormous volumes by the gravitational pulling of a larger neighbor. Some appear to have very little dark matter. Others seem to have dark matter but little else. They exist in clusters and in the field. They drift through space, enormous in extent, nearly invisible. There is something peaceful about that image, a galaxy that occupies enormous space, that has existed for billions of years, that goes about its slow, quiet existence, almost entirely unnoticed. At the opposite extreme are ultra-compact dwarf galaxies, tiny systems, just a few hundred light-years across, packed with millions or even billions of stars. These dense little objects are thought to be the stripped remnant cores of larger galaxies that were tidally disrupted by a larger neighbor. All the outer stars pulled away, leaving only the dense central nucleus behind. They are, in a sense, the compressed memory of something much larger, the heart of a former galaxy still shining, still carrying the gravitational record of what it once was. And there are galaxies shaped by the aftermath of extraordinary collisions, ring galaxies, where a smaller galaxy has punched directly through the center of a larger one, sending a wave of compressed gas rippling outward through the disk. The wave triggers a ring of intense star formation, and the galaxy becomes a brilliant, roughly circular band of new stars, surrounding a depleted center. The Cartwheel Galaxy, visible in deep images of the southern sky, is a textbook example. A golden nucleus surrounded by an expanding, luminous wheel of newly born stars, the aftermath of a head-on collision that happened hundreds of millions of years ago. The variety of galactic forms, the spirals and elliptical stars, ghosts, and compact remnant nuclei and rings and polar rings, and all the rest, reflects the enormous variety of histories that galaxies can have. Each form is the result of a particular sequence of events, particular mergers, particular feedbacks from central black holes, particular rates of star formation and quenching. No two galaxies have identical histories, just as no two rivers have identical courses, even if they flow through the same kind of landscape. And just as a river is shaped by the terrain it flows through, and in turn shapes that terrain, a galaxy is shaped by the cosmic web it inhabits, and in some small way shapes that web in return. The connection between the large and the small, the local and the cosmic, runs in both directions. You are part of that web tonight, in a very small way, in a very particular location, embedded in a spiral arm of a galaxy that is itself embedded in a local group, embedded in a supercluster, embedded in the cosmic web. Everything is connected to everything else by invisible threads of gravity, across all scales simultaneously. That connection is not abstract. It is real. The gravity of every object in the universe acts on every other object, however faintly. You are gravitationally connected to the Andromeda galaxy, to the Virgo cluster, to the most distant quasar. The force is immeasurably small at those distances, but it is not zero. Nothing is entirely isolated from anything else. The universe is one system, vast and intricate and continuous. Take a slow, easy breath. Let your body be still. Let the day go further away. There's a particular kind of peace that comes from spending time with very large things. Not the peace of having solved a problem, or finished something, or arrived somewhere. The peace of having briefly held, in the mind's loose and gentle grip, something too large to fully hold, and having that experience remind you, gently, of your own appropriate size. The peace of proportion, of scale, of knowing that the universe has been at this a very long time, and will continue long after anything pressing on you tonight has resolved itself completely. Galaxies offer this kind of peace. Let's stay with them for a little longer, drifting through what happens when we try to see the most ancient ones, and what the act of looking outward into the cosmos actually means in terms of time. Light travels at a finite speed, approximately 300,000 kilometers per second. This is the fastest that any information can move through space. It is a fundamental limit of the universe as we understand it. And it means that when we look at any object in the sky, we are not seeing it as it is now. We are seeing it as it was when the light that is currently reaching our eyes departed on its journey. For nearby objects, this delay is trivial. The moon's light is about 1¼ seconds old when it reaches you. The sun's light is about 8 minutes old. The nearest star beyond the sun, Proxima Centauri, is about 4¼ light years away. So the light from it is about 4 years old. But for galaxies, the delay is enormous. Andromeda's light is 2.5 million years old. The light from the Virgo cluster is about 50 million years old. And the light from the most distant galaxies observable with our best telescopes has been traveling for 13 billion years or more. When the James Webb Space Telescope captures an image of a galaxy that existed when the universe was only 400 million years old, it is not seeing that galaxy as it is now. It is seeing it as it was 13 billion years ago. The galaxy itself has continued to evolve over all that time. It may have grown grown enormously through mergers, or been disrupted, or been consumed by a larger galaxy, or turned into a quasar and back to quiet, or done any number of things in the 13 billion years since that light left it. We are seeing its past. And from many galaxies at many different distances, we can piece together a kind of retrospective, a history of the galaxy population written in light that left its sources at different moments in cosmic time, all arriving at our instruments simultaneously. Telescopes, in this sense, are time machines. Not in the science fiction sense. We cannot travel through time, cannot communicate with the past, cannot change what has happened. But we can observe the past directly by collecting light that has been traveling since ancient cosmic epochs. Every deep image of the sky is a layered record of the universe at many different ages simultaneously, from nearby galaxies a few million years in the past to distant ones more than 13 billion years in the past, all superimposed in a single photograph. The James Webb Space Telescope has extended this retrospective deeper than any instrument before it. Its sensitivity to infrared light, the long wavelength radiation that distant galaxies are redshifted into by the expansion of space, allows it to see galaxies that formed in the first few 100 million years after the Big Bang. Some of the galaxies it has found are more massive and more structured than models had predicted they should be at such early times. Why that is, whether it means our models need revision, or whether there are observational subtleties not yet accounted for, is still being worked out. Science is always being worked out. There is never a moment when the picture is complete, and that is not a weakness. It is the nature of an inquiry into something as large and complex as the universe. Each answer generates new questions. Each new instrument opens new puzzles. The process of knowing and the incompleteness of knowing are not in opposition. They are the same process. You can let that be true about other things too, if you like. Not every question needs to be resolved tonight. Not every open thing needs to be closed. Some things can simply remain open, floating gently, without urgency. Let's spend a moment thinking about the future of galaxies. Not to dwell on any of it with concern, but because there is something quietly beautiful about the long view, and holding it sometimes helps the immediate present feel lighter. The immediate future of our own galaxy. The next few billion years includes the merger of the Milky Way with Andromeda. Astronomers have measured Andromeda's approach with great precision. It is moving toward us at roughly 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will begin their first pass through each other. Their dark matter halos will begin to overlap and interact. Long tidal tails of stars will arc out into the space around them. Star formation will surge in regions where gas clouds from both galaxies collide and compress. The merger will not be a sudden crash. It will be a slow gravitational dance, a series of passes, each one more deeply entangled than the last, unfolding over hundreds of millions of years. Our solar system will almost certainly survive, displaced from its current orbit into a different region of the new merged galaxy, but not destroyed. The stars are simply too far apart from one another for stellar collisions to be a significant risk. Over time, the two galaxies will settle into a single, larger system. Astronomers sometimes call this future object Milkdromeda, or Milkomeda, a name that will probably never be formalized, but that has a kind of gentle imagination about it. The spiral arms forms of both galaxies will be gradually scrambled, the combined system will likely settle into an elliptical shape. Smooth, rounded, its star formation largely finished, an ancient, quiet giant, built from two old spirals that drifted together over the longest of all possible time frames. The sun will still be shining at that point, though it will be noticeably older and somewhat brighter. The cosmic events will be playing out on timescales that dwarf any human concern. This is simply the next chapter of a story that began 13 billion years ago, and will continue for far longer than that. Further into the future, hundreds of billions of years from now, the picture changes more profoundly. The stars currently forming in galaxies are using up the universe's supply of hydrogen. Star formation does not have an unlimited fuel source. Over vast timescales, the rate of star formation across the universe will slow. The brightest, most massive stars will have already died, leaving behind neutron stars and black holes. The medium-weight stars like our Sun will expand into red giants, and then cool into white dwarfs. Even the most long-lived, smallest stars, the red dwarfs, some of which can burn for 100 billion years or more, will eventually exhaust their fuel. On timescales measured in tens of trillions of years, the universe will grow darker. The galaxies will still exist, filled with stellar remnants. White dwarfs cooling toward invisibility, neutron stars spinning slowly down, black holes. The cosmic web will still be there, stretched thinner as the expansion of the universe continues. But the warm glow of active stars will fade. It will be a quieter universe, full of fading embers. But that is so far from now, so inconceivably far. The word now, in your ordinary daily sense, and the word now, in the context of that distant future, belong in completely different categories. Tonight the universe is alive. The galaxies are shining. Stars are being born in clouds of gas. Somewhere in the universe, a planet is warming in the light of a young star. The cosmic web is still assembling itself. We are here, now, in the bright part of the story, in the era of stars, in the age of galaxies. There is something quietly precious about that. Now let's think for a moment about what the Milky Way looks like from the inside, not from the grand imagined vantage of a distant observer, but from the particular, intimate perspective of someone who actually lives here. We cannot easily photograph our own galaxy from outside because we are embedded in it. We can photograph other galaxies, point a telescope at a sufficiently dark patch of sky, and you will eventually see a spiral galaxy, or an elliptical, or a pair locked in a slow gravitational encounter. But the Milky Way we know from the inside out. We see its broad disk as a faint, diffuse band of light across the sky on the darkest nights. The combined glow of hundreds of billions of stars too distant to resolve individually, pooled into that soft smear that ancient people in every culture gave a name. Looking toward the center of the galaxy, toward the constellation of Sagittarius, we are looking toward the densest, most ancient part of the Milky Way. The stars there are packed more closely. The gas and dust are thicker. The light of the galactic core is almost entirely blocked by intervening clouds of dust, which is why we cannot see the central bulge in visible light, but in infrared and radio wavelengths that pass through dust as easily as sound passes through a thin wall. The inner galaxy becomes visible. Stars orbiting the central black hole at speeds of thousands of kilometers per second. Clouds of gas being star's occasional, brief flares. Ancient, densely packed star clusters moving in complex orbits through the bulge, looking outward from our position. Away from the center, toward the outer disk, the galaxy thins. The spiral arms, marked by regions of star formation, glow with the blue-white light of young massive stars and the red-pink of ionized hydrogen nebulae. Between the arms, the disk is quieter, older stars, less active, less dramatic. And beyond the visible disk, the diffuse outer halo stretches enormous distances, populated by a sparse scattering of very old, metal-poor stars, and by globular clusters, dense, spherical gatherings of ancient stars that orbit the galaxy like satellites, some of them nearly as old as the universe itself. Those halo stars, and the globular clusters they travel among, are among the oldest things we can observe directly. Some of them formed when the Milky Way was still assembling itself, in the earliest epochs of its existence, when it was a much smaller, more chaotic system being built piece by piece through the merger of smaller proto-galaxies. The orbits of halo stars today carry the memory of those early mergers. They move in loops and arcs that are the gravitational echoes of the direction and speed at which their original host galaxy fell into the growing Milky Way. And the galaxy has not stopped growing. Running through the halo right now are stellar streams. Thin, curving ribbons of stars that were pulled free from small companion galaxies by the Milky Way's tidal force. The most prominent of these is the Sagittarius stream, a long arc of stars being stripped from the Sagittarius dwarf galaxy, a small companion currently being slowly digested by our galaxy. The Sagittarius dwarf has already passed through the Milky Way's disk multiple times, each pass drawing more stars away from it, and its remains now form a great loop around the galaxy, visible to patient astronomers willing to map the positions and velocities of thousands of individual stars. There are other streams too, older, more diffuse, some of them barely detectable even with the most powerful surveys. Each one is the remnant of a small galaxy or star cluster that was disrupted, its stars scattered into a long, thin arc that persists for billions of years before gradually mixing into the general halo population. By mapping these streams, astronomers can reconstruct the Milky Way's merger history, tracing back through time to identify which smaller galaxies have been absorbed, when and from what direction they fell in. It is detective work conducted in light and velocity, piecing together a past that left no direct witnesses. The full story of how the Milky Way grew is still being assembled. The Gaia space mission, launched by the European Space Agency in 2013, has been measuring the precise positions and velocities of more than 1 billion individual stars in the Milky Way with extraordinary accuracy. From that vast dataset, astronomers are identifying streams, substructures, and kinematic groupings that reveal past mergers in unprecedented detail. The map of our galaxy's history is becoming more complete, one star at a time. This kind of work, patient, detailed, accumulating slowly over years, has a quality that feels appropriate to the small hours of the night. Not demanding, just the careful, quiet building of understanding, one observation at a time, one paper at a time, across the long, patient project of knowing where we are. Let that patience be something you carry into sleep with you. Now let's think about what is happening right now in the science of galaxies, not to give you more to process, but because there is something calming dark, astronomers using the James Webb Space Telescope are continuing to study the most distant galaxies, refining our understanding of how structures formed in the early universe. Each new observation adds a little more detail to the picture. Each surprise, and there have been many, prompts new thinking, new models, new questions to investigate. The work is not frantic. It is methodical, careful, cumulative. Meanwhile, underground laboratories in several countries continue to operate their dark matter detectors, extraordinarily sensitive instruments cooled to temperatures near absolute zero, waiting in the quiet for the faint signal that would indicate a dark matter particle had interacted with their detectors. Each generation of detectors is more sensitive. Each null result provides information and narrows the range of possibilities. Gravitational wave observatories, LIGO in the United States, Virgo in Europe, listen for the ripples in space-time produced when massive objects collide. Black holes merging, neutron stars spiraling together. Eventually, the hope is to detect the background hum of gravitational waves produced by all the black hole mergers that have occurred across the history of the universe, a kind of cosmic memory encoded in the fabric of space-time itself. Large galaxy surveys, the Dark Energy Spectroscopic Instrument, the Vera Rubin Observatory, the Euclid Space Mission, are mapping the positions and movements of hundreds of millions of galaxies across the sky, with the goal of tracing the history of cosmic expansion and understanding the distribution of dark matter and dark energy. These surveys are building the most detailed maps of the universe that have ever been constructed. All of this work is happening slowly, steadily, in the background of ordinary human life. Telescopes turning in their domes, detectors waiting in the dark, computers processing data, scientists reading papers and writing new ones. The universe keeping its secrets for now, sharing them gradually, in pieces, to those with the patience to wait. There is something of the long view in all of this. The universe has been doing what it does for 13.5 billion years. The science of understanding it has been underway for a few centuries at most, and modern observational cosmology in its current form for only a few decades. We are very early in the project. The map is mostly blank. The questions are mostly open. That is not a failure. It is simply the present state of things. And it will improve, slowly, over generations. The scientists working today are building the foundation on which scientists of the future, decades, centuries from now, will stand and see further. You can let that thought carry you gently, the sense of a very long, patient enterprise, moving forward in the dark, quietly confident that the universe is worth understanding, even if understanding it takes longer than any single lifetime. And now, as your breathing has slowed even further, as the details of dark matter and gravitational waves and starburst galaxies have begun to soften and blur at the edges of your attention, let's zoom very gently back out. From the equations and the surveys and the underground detectors, back out to the simpler, quieter truth that started this whole journey. Above you, right now, the sky is full of galaxies. Not in a way you can see from inside a building, or under the glow of city lights, or on a cloudy night, but they are there nonetheless. They have always been there. Every clear, dark night, every point of sky between the stars holds more galaxies than you can count, each one a system of billions of stars, each one with its own history of mergers and star formation, and dark matter and ancient light. The universe is not empty. It is full, enormously, quietly, overwhelmingly full. of structure and history and ongoing change. And you are inside all of it, right now, breathing gently, in a small warm room on a planet that orbits an unremarkable star, in one of the spiral arms of one of hundreds of billions of galaxies. That is an astonishing situation to be in. It's also perfectly ordinary. This is simply where you are, where we all are. Part of something incomprehensibly large, and somehow also just here in this moment, in this night, in this particular small window of cosmic time. You don't need to figure out what that means. Nobody does. The philosophers and the physicists and the cosmologists and the poets have all been turning that question over for as long as there have been humans capable of asking it. And the answer, if there is one, hasn't arrived in a neat form that fits easily into the mind. What arrives instead is something softer, a sense of proportion, a recognition that the things that pressed on you today, the worries, the to-do lists, the half-finished thoughts, are very small against this backdrop. Not meaningless, but small. And small things can be put down, just for a night, without anything important being lost. The galaxies will still be there in the morning. The universe will have continued exactly as it was going to continue, regardless. Sagittarius A star will still be sitting quietly at the center of the Milky Way. 4 million solar masses of invisible density, affecting nothing tonight, being affected by nothing tonight. Andromeda will have moved an infinitesimally small fraction of a light year closer, as it does every year, its trillion stars continuing their unhurried approach across 2.5 million light years of space. The dark matter halos of both galaxies will still be there, invisible and essential, holding everything in their quiet gravitational embrace. And somewhere, in the darkness between filaments of the cosmic web, in the long empty corridor of a cosmic void, a lone galaxy drifts. Perhaps it was ejected from a cluster long ago. Perhaps it formed in that quiet region from the very beginning. It has no neighbors close enough to disturb it. Its stars form slowly, calmly. Its spiral arms, if it has them, turn at a pace so gradual it would take hundreds of millions of years to notice any change. It is simply there, alone in the dark, held together by the gravity of its own mass and the invisible halo surrounding it. Going about its business at the pace of galaxies, there is a certain peace in that image. A galaxy alone in a void, simply existing. Not striving toward anything, not measured against anything. Just present, luminous in its small way, doing what it does. You can be something like that tonight. Present. Still. Not measured against anything. Just breathing, just resting, just here in the gentle dark. Let the details of everything we've talked about blur softly now. The names, the Fermi bubbles, Sagittarius A star, Laniakea, the cosmic web, dark energy, dark matter, the James Webb Space Telescope, Type I supernovae, whims, actions, tidal tails, starburst galaxies, ram pressure stripping. Let them drift like embers cooling in the night air. They don't need to stay. The feeling behind them can stay, if it wants to. The sense of scale, the sense of age. The sense that the universe is vast and patient, and fundamentally at ease with its own incompleteness. That feeling doesn't require any particular fact to anchor it. It is just what arises when you spend time thinking, gently, and without hurry, about where you are. You are in a universe that has been building itself for 13.5 billion years. You are on a planet that formed about 4.5 billion years ago from a cloud of gas and dust that was itself the remnant of older stars. You are made of atoms that have existed far longer than the solar system, cycling through stellar interiors and interstellar space and planetary surfaces, and living things over timescales that dwarf every human measurement. You are, in the most literal sense, made of the universe. Carbon forged in stellar furnaces. Oxygen blown into space by ancient supernovae. Iron that has circled through star after star across billions of years. All of it assembled, extraordinarily, into something that can lie still in the dark and wonder where it came from. And right now, that something is resting. Let your body be heavy and still. Let the muscles in your face relax. Let your breathing settle into whatever rhythm is natural and easy. There is nothing to maintain, nothing to monitor. Your body knows how to rest. It has always known. Let it do what it knows. The great questions of cosmology will still be there in the morning. The dark matter will still be invisible. The distant galaxies will still be receding. The James Webb Space Telescope will still be gathering ancient photons in its steady, patient orbit. The scientists will still be working. The universe will still be expanding. And you will have rested. And that will be exactly right. If these quiet journeys help you rest, you are always welcome to return to deep somna whenever the night needs company. The galaxies are patient. They will wait. Sleep well.